Good morning and welcome to Sunday of week 1 of your Physics 5 a day, and today we're moving on to motion and we're starting with vectors and scalars. Vectors are quantities that have size and direction, whereas scalars only have a size. So for the vectors, the most obvious one is force. You can't have a force without a direction. It has to be in a particular direction. But the others that you want for your A-level are those. So you only need to know 5 vectors for your A-level. The scalars is basically everything else that you do for A-level. So mass, distance, speed, time, energy, temperature, so on and so on. So you know loads of scalars. Okay, but so what? What difference does it make? Well, the difference is that if you add up scalars, you can only get one answer. So for example, energy. If I do 6 joules plus 10 joules, I can only get 16 joules. There's no other possible answer. Whereas if I'm adding up forces, if I'm adding up, say, 6 newtons and 10 newtons, well, I can get lots of different answers. I can get an infinite number of different answers. So if I do 6 plus 10 in the same direction, I get 16 newtons in that direction. If I have 6 in one direction plus 10 in the other, I get 4 in the other direction. And if I can do it any way I like. So 6 newtons down, 10 newtons to the right, that's going to get me about 12 newtons at an angle of about 59 degrees to the vertical. So the difference is, why do we care? Why do we care if something's a vector or a scalar? It's this. It's that if you add up scalars, you are going to get the same answer every time. But vectors, depending on which direction they're in, it's going to affect the answer when you add them together. It's worth taking a moment to talk about distance and displacement. Distance travelled is, we can think of it as the length of your path. So if you go from your house to the park, so we're going to drive. So we're going to drive from our house to the park, then to the cinema, and then back to our house. So our total distance travelled is the total length of that path. But our total displacement travelled is where we are relative to our starting point. So if I drive to the park, to the cinema, and back to the house, my total displacement is 0, because relative to where I started, I haven't gone anywhere. Distance, your total distance travelled, that affects things like how long you're out, how much petrol you use, the cost of your journey, and your total displacement, well, that decides where you end up. So you can see that these quantities, they are different. There's a reason why we have the difference. The symbol for displacement is S, and when you graph it, you need a different graph for every direction. So, for example, if this was my forwards and backwards motion, I'd need another graph for my sideways motion and another graph for my up and down motion. Okay, and here, 0, 0, that is where you start from. That's your starting position. And then you have to make a decision about which way is going to be forwards. So, for example, if this is my start position, I might decide that positive is going to be going forwards from my start position and negative is going to be going backwards from my start position. Or if you're doing upwards and downwards motion, I might decide that positive from my starting position is upwards and negative from my starting position is downwards. But it's up to you which way around you do it. Okay, so let's say that here's me in my start position. I am downstairs in my house, and then I walk upstairs to the first floor, and then I immediately walk back down again to the downstairs, and then I go down into the basement. So I'm below my starting position, and then I go back up to the downstairs. That's what my displacement time graph would look like. Notice that my distance time graph simply logs how far I've gone. So in this version, I would go that far to go upstairs, and then I'd travel that far again to come back downstairs, and then I'd travel that far again going down into the basement, and so on. I can't quite fit it on there. Our other important pair of quantities is speed and velocity, Speed is just how many meters per second you're doing. It doesn't matter what direction. So the speedometer on a car, it doesn't matter if you're going forwards or backwards, it's still going to just give you how many meters per second you're covering. But velocity, if we say that forwards is positive, then when you're travelling backwards, your velocity will be negative. Don't forget about the difference between speed and average speed, velocity and average velocity. So yes, in our previous example where we go from the house to the park to the cinema and back to the house again, the total displacement is 0, so the average velocity is also 0 for that journey. So when you plot velocity on a graph, again you have one graph for each direction. So here I'm going to have just my upwards and downwards motion on this graph, and again you have to decide which way is going to be positive and which is negative. So I'm choosing that positive is going to mean you're moving upwards and negative is going to mean you're moving downwards. So if I think about a ball being dropped, hitting the ground, bouncing back up again, its speed time graph would look like this. I drop it here, it accelerates, it's moving faster and faster and faster, it hits the ground, it bounces back up with the same speed, and then as it goes up, it slows down until its speed is 0 again when it gets back up to its maximum height. But for the velocity, when I drop it, it moves downwards first of all, getting faster and faster and faster. And then when it hits the ground, it bounces back with the same speed, but it's moving upwards. So let's say, I don't know, let's just say that was 5 meters per second downwards. Then when it leaves the ground, it's going to be, I'm assuming it's not losing any energy here, so it's going to leave the ground travelling at 5 meters per second upwards. So we do draw like a basically vertical line there to join the two. So it leaves the ground travelling 5 meters per second upwards, and then it slows down as it gets higher until at its maximum height it's travelling at 0 meters per second again.